Okay, so today's lecture is going to be related to these two main topics. One is the matched filter, and the other one is correlator. Okay, so we spend this lecture today about these blocks at the on the received side, and hopefully we have some time for Simulink and to do simulation for the whole system. Okay. So if you remember during the last few lectures, we spent a lot of time talking about probability distribution functions. In essence, to characterize the random variables. We also talked about some random number generators that can helps produce the pseudo-random integers, for example. Okay, and on the video from the last lecture, because last week we didn't have any live lecture, so I asked you to look at the videos, right? So during last lecture, on the video, we looked at the random processes and how the statistics and and the types of random processes that we looked at last time. Okay, Thirarat, can you tell me what are the types of random processes that was in the last videos related to the stationary random processes?
Strict sense stationary and wide sense stationary.
Okay, and
Okay.
now and what are the differences?
For strict sense stationary, the all order does not depend on time, but for wide sense stationary, only the first and second order do not depend on the time
Second and
Second and
first and
first
second
and
order
second
of
order
what?
of of statistical average.
Yeah.
Yeah, yeah, yeah.
Okay, good. Okay, so when we talked about the wide sense stationary random processes or strict sense stationary random processes, we are talking about the statistical averages. We are not talking about the time average. Okay, and of course, in practice, it's gonna be so difficult to look at the statistics or the averages at all orders because we need the joint PMF or joint PDF of all orders as well, right? Okay, and so can I ask Pio? So what's the significance of the Gaussian random processes or Gaussian random variables in terms of these properties? You can talk about the uh, correlatedness, independence, or you can talk about this stationary property.
Stress and stationary is dependent on the Y-sense stationary, but Y-sense stationary does not depend on the stress sense. Does not correlate it, with the stress sense.
Well, that's in general. How about the for Gaussian random variables?
I don't know how to explain it.
Well, in general, I mean there are two types of proper. There are two approaches of properties that we look at, right? One
Yes,
is related to uncorrelatedness and independence, right?
yes,
In general, if we know that random variables are independent,
yes.
some random variables are
Because,
independent. It
yes.
Yeah, that implies uncorrelatedness, but not otherwise, right? Except for the Gaussian random variables, uncorrelatedness implies independence as well. Okay. Meaning that if we know that we have some multiple Gaussian random variables which are uncorrelated, that implies independent as well. Yeah. So that's what we mean. And similarly, for stationary random processes, it's also true. In that, for the Gaussian random processes, if we know that they are, if we know that they are Wisen stationary, it also implies strict sense
It's a
stationary
stationary.
as well. Yes, but in general, that is not true, right? So in general, if you know that any random processes, if it is strict sense stationary, it implies Wisen stationary, but not vice versa.
Yes.
So that's what we meant. And what else? And what is the power spectral density? Can anyone tell me how do we find the power spectral density from the last lecture? Okay, uh, to find the power spectral density, we only do it for Wisen stationary random processes. So when we know, so this is, let's represent at xt, okay? So if we can find Rx tau, where tau is a time lag, then, but this is the Rx tau from the statistical averages, okay? Of course, in MATLAB, or in any chip design, we don't have any statistical averages, right? We just have time average in general. And so when we know the autocorrelation of the random processes, we can find the Fourier transform, and that will give us the power spectral density. Okay, so that's about it last time. And I think the last time there was the last part of last lecture. It was about what happens when the random processes, which are Wisen stationary, if they are passed through an LTI system, for example, filtering or any linear circuit. Okay, then so we find that the output is still also Wisen stationary random processes, and the mean and the variance, the mean and the power spectral density can be found accordingly. And I think last time we did this, my is equal to mx multiplied with h of 0, okay, where h of 0 is the DC of the linear system frequency response. And also for the power spectral density of the output is, what is it? Magnitude of HF square multiplied with power spectral density of the input. Okay, so these are the main results from last time. Okay, so this today we are going to come back to what we were left off from the last 2 or 3 lectures, because we spend a lot of time looking at the what is it, the noise and the random variables, right? So today we'll come back to a system. So what are we going to look at? So let us consider a simple communication system with with an additive. This represent additive white Gaussian noise channel. Okay. So whenever we talk about transmitting some data bits, modulated, this is modulation. Okay. And so it becomes pulses, and then we transmit through AWGN channels. Whenever we talk about this, it means that we focus our scope on on the channels with bandwidth unlimited. Okay, or in a way it's an ideal channel. Okay, However, in general, the channels, have a limited bandwidth and also not ideal. But when we talk about some modulation scheme and also how to demodulate it or detection for modulation like this, oftentimes we only look at the AWGN channel. Okay. Later on, we'll look at the channel with limited bandwidth and also with white Gaussian noise as well. Okay. So this is a simple communication system, and in this case, it is just a NRZL. Okay, and also, so you see that for NRZL for bit 0, we just transmit the very simple square wave, okay, of the negative amplitudes, while for the bit 1 we transmit the square wave of the positive amplitudes, okay, and uh, and the length is the TB, okay. So that means that the energy is the EB. Okay. When we talk about this, let me go through a little bit of information in here. Okay. When we talk about different pulses for each bit, it means that for E0 and E1, okay, so we have the energy for each bit depending on bit 0 or bit 1, okay. And if you look from here, like very simple look at what is the energy of the bit 0, tirarat, tirarat. Mm.
Uh,
To find
To find
energy,
energy,
you just
you just
square the
square the
amplitudes,
amplitude
and then
and then
oh,
just
just
find the
find the
area
area
under the
under the
graph.
graph.
Yes.
TB.
Yeah. So
Yeah,
this one
so
is
this
TB, right? Because it's 1 times TB. How about E1?
TB as well.
Also the same, right? Yeah. So E0 and E1, they are both equal, which are TB joules. So when we talk about the average energy per bit, EB is like an average energy per bit. Okay. So it's basically E0 plus E1 divided by 2, which is TB. Okay. So that's what we mean by average energy per bit in general. Okay. And so this is, and also if you look at the system below, okay, depending on we look at, but in general, let me look at it as, so this part is the let me see, maybe not a good way to look at this. One moment. Uh, where's my eraser here? Oh, here. Maybe I should draw like this. Okay. So this side is the transmit side. Okay. And this side is the receive side. And in the middle is just channel. Okay. So very standard way of looking at it. Okay. And if you take a look here, in this case, so on the transmit side, we have average energy per bit equals to TB, right, joule. And then on the receive, and then for the channel, this is the Gaussian noise, Gaussian random variable with the n like this, which represent the normal distribution with the mean of 0 and also the variance of sigma squared. Okay. Where sigma squared can be represented from last time in 0 over 2 watt per hertz. Okay. This is thermal noise, so it's related to temperature in general. So we say that in this system, the digital SNR is equal to EB over N0. Or sometimes some people say is the EB over sigma square. Okay. But I think this one is more common to see. Okay. Okay. So that's part of it. Okay. And next one, let's take a look at these slides. So when on the receive side, we can find the quality of the receive signal using something so-called eye diagram. Okay, the eye diagram will helps indicate the signal qualities on the receive side. Okay, on the receive side. Okay, and and how is it constructed? Let me say that the eye diagram is a very crude way of not a crude way, but is a very simple way of detecting the signal quality. Okay, and it can be used, from the very early part of looking at pulses on the scopes uh, on the scope that we look at. And in essence, what it does is the eye diagram is constructed by an overlay of one or two periods of pulses, right? Meaning that, let's say that we have this type of perfect or ideal no noise pulses like this, so we have like, this is for NRZL, okay? Although it can be used for any pulses. This is an RZL. So this is like a ideal pulses. Okay. So eye diagram represent, on the left side. We can construct it from one period, or we can construct from two periods of the pulses. Okay. So we can just put whatever we have on the left hand side, and we can just overlay all the pulses. Okay. Let's say we want to overlay 10 bits. We just overlay 10 bits. Or we overlay 20 bits, but for two periods, we just do it for 20 bits on the rightmost figure. Okay. However, in practice, when we transmit information, because of the band limited channels or some other distortion, so our signals may appear something like this. They may not look like square wave like what we want. Okay. So in this case, if you, let's say, you put these two pulses that we receive here, okay, and overlay all over each other. Okay, so we will have a shape like this. Okay, we can also do two periods, which is on the leftmost, on the rightmost figure. So we have positive and we have negative, etc. Okay, but we have to do more than just one bit, 2 bits, or 3 bit, 4 bits. We do like multiple, maybe hundreds of them or whatever, depending on the windows that we are looking at. Okay, so you see that, uh, when we send pulses like this, or like on this side, okay. Actually, this one doesn't have any much distortion. We intentionally transmit it, so you see that, these figures, they look like eyes. Okay, that's why we say it's the eye diagram. Okay, and then on the lower panel or the bottom figure, you see that, this graph, they have like some type of distortion. They don't look nice at all. And this is even without noise. Okay. So if we, for one period eye diagram, we just look at each period and we just overlay them together. Okay. And we'll get something like this. Okay. If we do two periods, we look at two periods at a time and we overlay together here. Okay, so this is also the eye diagrams. And if we don't have so much distortion and we don't have so much noise, so the eyes will look very large. Okay, if the distortion is very high, then it means that the eyes, they tend to like to close, you know. So this is what we call by eye diagrams. So for the eye diagrams, they can be used for indicate signal quality like noise levels, you know. Are there lots of noise? Are there lots of interference, distortion or not? Okay. And also, we can also look at the, how do you call it? Um, the sampling, the optimal sampling instant. Okay. For example, if we look here, okay, if we expect to see zero, intersect, the zero amplitude, intersect here, but this zero, they shift to the right or to the left too much, it means that when we do sampling, it's not so good. Okay. So eye diagrams can be used for different things. Okay. So let's take a look. I think I'm a bit slow again. Always, no? Okay. So for a simple communication system like this, how do we make a detection? Okay. So this is RT, which is a received signal. Okay. In general, the signal will be noisy because of the noise in the system. Here, I don't put any effects of the bandwidth limitation, so it's not curved, so it's just noisy. Okay. So what can be used on the receive side? So all this is the receive side. Okay. Receive side. Okay. A simple way of deleting noises is using low pass filter. Okay. Thirarat, what is the difference between low pass filter and high pass filter?
Um, Low pass filter will filter out the low frequency signal.
Actually, on the contrary, you low pass filter means that it only allows low frequency components. Okay. It means it rejects high frequency components. Okay. You can just translate from the name by itself. It only allows the low frequency components to pass. Okay. So that means in this case, if you use a simple receiver or detector like this, all the high frequency components they disappear. So you only have like some noise remaining, but only low frequency part. Okay. And generally for digital communication system, whatever you use at the receiver or detector, no matter how complicated they are, at some point after that you have to have an A to D. Okay. So you will convert from any continuous signal into discrete signal. And then from here, let me call it ZI. Okay. So whatever you get here, then you will do a threshold detector or comparator to make decision. We put hat like this, it means decision. Okay. To get to get decision of the transmitted bits. Okay, so you see that so this is, although this is a very simple receiver, it is actually characterize and represent the gist, the heart of the digital communication system in general. Okay. So you see that on the receive side, we do this detection, we are not trying to duplicate or reconstruct the transmitted signal. Okay, we just trying to make decision what the transmitted bits or symbols are. Okay, do you get what I'm saying? Tirarat, Pyo, and Tananpat. You get what I'm saying?
Yes.
Okay, so we're not trying to duplicate or reconstruct transmitted signals. Okay, we're just trying to make decision of what the bits and the symbols are. Okay, so keep this in mind. So in the, of course, after you make decision, you can reconstruct, but maybe some bits are incorrect, so you don't reconstruct them correctly anyway. Okay. And okay, so let's take a look at next one. So this is the Simulink system that we are playing with today. We'll use this as a base Simulink system that we can play around with. Okay. So let me show. So I think you are familiar with this system already, but because we haven't come back to this for some time, no. So on the transmit side, you know this already. So in this case, we use NRZL, but we can use some other thing, no. And we added noise to it. On the receive side, this is the receive side. Okay. So we can have a low pass, we can have a filter here, which we can change the coefficients so that they become low pass filter, simply by just put like all ones, depending on how long this is, divided by square root of n. Okay. So this is one way of doing it. And I think before the lectures on random processes or random variables, we also construct here by using some type of filter also, right? We also use filter block as here in order to generate like different types of modulation scheme. Okay, but it's a simple one. Okay, and on the receive side, if we construct with the receive side with low pass filter, that's all we do, depending on how long it is. And we have a to D, and then we have comparator. Okay, that's, and this is like a very simple. Okay, so the question to this lecture is, what is the optimal detector? Okay, as we learn later that using just a low pass filter on the receive side is not optimal. Not optimal. You may ask, what do you mean by optimal? Okay, we'll talk about that in a minute. Okay, so basically for this system, we have data bits, we have modulation, so we have pulses that we transmit. We have noise because this is the AWGN channel. Okay, and then we have the receive signal. The question is, what is the optimal detector that we should use on the receive side? Okay. Okay. To derive the optimal detectors, maybe you can guess, because in this lecture we are talking about the two types of optimal detectors. One is called the meshed filter, and the other one is called correlators. Okay. So let's look at this as a formal statement. So if we are given the pulses SIT, okay, where I is represented by 1 all the way to M, and T is in the range from 0 to T, big T, okay, meaning that it has limited amount of time. And there are M types of pulses, depending on whether they are binary or non-binary. If M is equal to 2, then there are only two types of pulses that are transmitted, okay? Then we added noise, and then if the detector is a linear system, a linear time invariant system, with the impulse response of the detector as HOT, or the or the spectrum of frequency response of H0F. Okay. The question is, how do we design the detectors for the digital pulses? Okay. And basically, in order to design the detector, we just need to find the H0F or H0T that is optimal. Okay. So let me see how deep should I get in here. I think I want to get a little bit deep so that we all understand completely. Okay. So in this system, let's take a look together at it together. If we send the pulse SIT, the energy, let me call EI, can be computed from square of the pulses from 0 to t. Okay, this is a very standard formula for energy. Okay, or in the Fourier transform, we can write it as the negative integration of negative infinity to infinity, the size, the magnitude of SF square df. Okay, where SF is the frequency spectrum or the Fourier transform of SIT. Okay. Then what else should I write here? Okay. For the noise, the power spectral density Gn of F is equal to sigma square. Okay. And at the output of the linear system, this spectrum of noise enters the system. So at the output, if we look at the noise part only, we have Gn prime F is equal to H0F square and then sigma square. Okay, this is from last lecture. Okay, this part from last lecture. Okay, I'm gonna write all this formula because on the next page they just stacked on each other. Okay. Also, if I look at the output here, okay, ZIT actually includes both the. Let me see how it's written. So ZIT here. So for the data part, okay. At the output of this detector, if you look at the data part, which is SIT, okay, is passed through this detector. So we can write ZIT, which is the data part, as SIT and then convolution with the HOT. Okay. If you don't remember this, you can go back and review this lecture or this topic on the signals and systems class for any linear time invariant system. Okay. If the input is the deterministic signals, we can find the output as the input does the convolution with the impulse response of the system. Okay. Or you can look at it at the inverse Fourier transform of the product of Fourier transform of the data signals multiplied with the Fourier transform of the optimal filters. Okay. So in essence, this is the ZIF. Okay. So what do we mean by optimal detector? So basically, we try to optimize SNR, okay, after A to D, okay, which is here. We want to optimize the SNR here at the 3 stars. Okay, there are many ways to optimize it, but this is a simple way of doing it. Okay. So what is the SNR at this point? I can write it as SNR T. Okay. T represent after the A to D. This will be equal to the data part through the detector square divided by sigma 0 square. Okay. Where sigma 0 square is just G and F. Okay. So this is what we want to optimize. Okay. You can optimize some other ways, but sometimes if you optimize the different parameters, then it's not easy to derive what we want. Okay. So you have any question about these slides? If you have question, please ask now, because for the next two slides, we will utilize these results and then derive the optimal detectors. You have any questions so far? If you do, please ask now. Let me see, what time is it? Okay. You have any questions so far?
No.
Okay. Okay. Anyway, so let's take a look more. If you have question, then we'll come back, no? So let's do a derivation of the optimal filter, and in this case, the optimal filter is actually called meshed filter. Okay. So step one, we will compute the SNR after A to D, which is SNRT equals to the data part that is passed through the LTI detectors divided by uh, the variance of the output noise at the back of the detector. Okay. So let's first look at the signal part, which is the top part. Okay. So for any filter or detector HT with the spectrum H of F in general, so we have that so at the output we have that ZIT. I wrote it already from last page. Okay, so I just want to write it again so that it's a little bit easy to follow. ZIT is SIT convolution with HT. So this is in general, so I don't put O at the subscript. Okay, and uh, if you look at the spectrum, ZIF is just SIF. Okay, because in Fourier transform, in frequency domain, the convolution becomes multiplication. Okay. So in a way, we can say that ZIT is just the inverse Fourier of ZIF, which is the inverse Fourier transform of, or let me write F clearly, okay? So we don't get confused with the T. SIF and then HF, okay? Also for Pyo and Tananpat, if you, I just want to tell you one more time that it's very common for us when we write in time domain, we use the lowercase. When we write in terms of spectrum, we often convert to capitalized letters, okay? That's all. So this is before the A to D. This is still time domain, right? So at the output of A to D, we have ZI, which is equal to ZIT, T equals to, let's say, at every period, okay? Or at every period of the bits, okay? So, okay. Also for the inverse Fourier transform, I can write this as integration of SIF multiplied with HF dF. This is the Fourier transform formula, okay? And oops, we have to multiply with the exponential term. which is e to the j 2 pi ft, and then the f, okay, from negative infinity to infinity. Sometimes instead of writing e to the j 2 pi ft, some people or in some textbook they just write it as e to the j omega t, where omega is 2 pi f. Okay. So if I write this equation, okay, and I look at only at the time of every period, okay, what am I gonna have? Okay, I'm gonna have this formula from the star, but I replace all the small t with the big T. So this is what I'm gonna get. Okay. The derivation takes some effort, but after we have the formulas that we can use, then it's more simple when we want to look at detectors. Okay, this is just part of the derivation. Okay, so that's the signal part. So we're gonna use these later. Okay, to put in the SNR formula. Okay, you can see that here we have Zi. So later we replace Zi with this whole formula. Okay. And next one is the noise part, which is the next page. So for the noise part, we have the PSD of the input noise. The input noise has the PSD of n0 over 2, which is sigma square. Okay, watt per hertz. Okay. So at the output, we have GN0 or G0F, whatever, which is equal to the uh, input PSD of the noise input. Okay, you can call this GNF. Okay, of the input noise input to the LTI system, which in this case is just a detector. Okay, and multiply with the magnitude of the uh, frequency of the detector square. Okay. Okay, so if you want to find the sigma 0 square, okay, what you need to do is you have to integrate the PSD, right? And in this case, we will do it in general. So we have n0 over 2, then integrate from negative infinity to infinity, n0 over 2, okay, and then the f. Okay. Then from here we can find this is the noise power. You can write it as Pn, no problem. Okay, so we can put this equation. Let me call this as a let me call this as a 3 asterisk. Okay, so we put the equation with 2 asterisk and the 3 asterisk in the formula for SNR at after the A to D. Okay. So for the top part, which is Zi, we will have this term Zi, but I'm going to put square over it. I'm going to have integration of, let me see. Okay. I'm going to have the integration of SF, HF, okay, and e to the j 2 pi ft square, okay. So if you take a look here, here is Zi, right? Okay, okay. But we have to square it. So I will put a magnitude, for simplicity later. And then divide it by the equation from the 3 asterisk, which is n0 over 2, integration from negative infinity to infinity, n0 over 2, okay, HF, and then df. Okay, this from negative infinity to infinity. Okay, so that's what we will do. Well, from here, maybe it looks a bit difficult, but if you look in the textbook, basically, we can use this relationship called Cauchy-Schwarz inequality, meaning that we can simplify the numerator on the last page. Okay, Cauchy-Schwarz inequality says that given two functions, if we have function f1x and function f2x, and if we have a magnitude of integration of f1x multiplied with f2x dx, the whole magnitude square, this one is less than or equal to the energy of each function multiplied to each other. Okay. This is in a way similar to the concept of triangle inequality. Okay, like in geometry, it's related to the idea of like what when you add when when you add two sides of the triangle section, it's less than or equal to the summation of adding the triangular section of each side. But this is in terms of function, so it's a little bit different. Okay. And the inequality on this equation occurs when f1x is equal to multiple of f2x conjugate. Okay, this thing is conjugate. Okay, this is not convolution, no, it's conjugate, because the f1x and f2x in general, they can be complex function. Okay, so we'll utilize this and do it on the previous page. This is what we will get. Okay, so we will let the first function to be hf, second function to be sif e to the j 2 pi f t. This is, note that this is capitalized. Okay. So we'll have that this magnitude of the multiplication of these two spectrum and exponential is less than or equal to integration of each function square. Okay, so this is from the Cauchy-Schwarz inequality. Okay, because the top part is less than or equal to these, or let me write this here. Okay, e to the j 2 pi ft df. Okay, but this term is the same as magnitude of SIF multiplied by magnitude of e to the j 2 pi ft. Okay. What is this equal to, Thirarat, this term? Magnitude of e to the j 2 pi f capitalized T. Let me write on the side here. Thirarat, can you express complex exponential in terms of cosine and sine, maybe? Okay. And we can do from there. Or can any of you can remember what is any complex exponential? How do you express in terms of cosine and sine? I think Thirarat can remember. It's a cosine of the angle 2 pi ft added with the j, which is the complex the number, and sine 2 pi ft. Okay, you can always express like this. Okay, so you can express complex exponential as the complex number which is cosine of the angle, and then plus j sine of the angle. Okay. Okay. So what's the magnitude of complex number? Thirarat.
Cos square plus sine square.
Exactly. Which is equal to
1.
exactly. Yeah. Cosine square of an angle plus sine square of an angle is equal to 1. Exactly. Yes. And that means this part is just 1. Okay. So when we write down here, we don't have any complex exponential in the formula at all. Okay. And then from the bottom side, we just put the sigma 0 square, which is the power of noise from the previous page. Okay. Because the numerator, this term is less than or equal to, so that means when we express as this term, this has to be less than or equal to. Okay. And then you notice that some terms can be cancelled out, right? Here, shoop, they can be cancelled out. Okay. So uh, what you will have is so this is will be equal to integration of negative infinity to infinity the magnitude of si square f df divided by oh no need to divide, no, we can just write it as 2 over n0, so that's all. Okay. Okay. So, and what is this? What is this? If you look from the previous page, this is just E energy, right? The energy of the pulse. I don't know, do I write ES here or just E? Let me see. Yeah, I just write it as E, right? Okay. So this is just 2E over N0, where E is the pulse energy. Okay. Okay, so it means that if we and so it means that the SNR will be always less than or equal to this term. Okay. SNR will be less than or equal to 2E over N0. And it is equal only when what? Is equal from the Cauchy-Schwarz inequality. Is equal when it is equal when H optimal F is equal to K times Si conjugate multiply with e to the negative j 2 pi ft. Okay. So the equality occurs when f1x is equal to k f2x conjugate here. Okay. So this, let me write on the next page. Okay. So if you take a look from the previous page, you notice that first of all, the maximum SNR only depends on the pulse energy and also the PSD of output noise. Okay, it doesn't depend on the pulse shape that we use. Okay, so that's the observation number one from the previous page. And secondly, the optimal filters will have the transfer function like this. Okay, from the Cauchy-Schwarz inequality. Okay, which says that the equality occurs when one function is multiple of the other function conjugate. Okay, when you conjugate the complex exponential from positive, it becomes negative, right? And for SIF, this one, we just put conjugate at the top because it can be anything. Okay. So it means that if we know uh, the spectrum of any pulse, the essential, the optimal detector for that specific types of pulse, it's just a multiple of them, but you have to conjugate. Okay. However, we also want to find the impulse response of this filter. It turns out that I'm not gonna go through all the properties from the top to the bottoms, but it turns out that this impulse response of the detector HOT can be found from SI capitalized T minus T, okay, which means that the impulse response of the detector that is optimal can be found, the shape of it can be found from flipping the pulse itself, with the vertical axis, because with the time domain, and then delayed by t second. Okay, so that's all, and we call this as a matched filter. Okay, so if we know the shape of the pulse that we transmit, we can just construct the detector that has a shape, that the impulse response has a shape very similar to the pulse that we transmit itself. Okay, but we have to flip first and delay. So the shape looks the same. You just flip it, and that's why it's called matched filter. Matched mean is it looks the same. Okay, so that's what we mean. And some from previous page, we also look already that the maximum SNR is equal to 2 over n0 multiplied with the energy of the pulse, or I can write it as E over n0 over 2. Okay. Yeah, incidentally, the maximum SNR is equal to the energy of the pulse, right? That we transmit, and the bottom part is the PSD of the noise, of the input noise. Okay. Okay. So now we are ready. So you have any questions so far? So I can explain slowly. Mhm.
Could you please go back to the previous slide?
Yeah, certainly.
Okay, thank you.
Sure. And this n0 over 2, in a way, this is, if you look, in terms of the spectrum, this is, how do you call it? This is we call it a two-sided power spectral density, or PSD. Okay. Okay. Which is the PSD of the input noise, the thermal noise in this system that we are looking at. Okay. Okay, maybe I go a bit slow on this, but keep in mind that when we look at the manual, or we look at how a modulation system, when they look at their performance evaluation, they always look at this type of E over N0 all the time. So they just hope that we know, where they come from and all that. Okay, so let's take a look then. It means that, so in this case, after this short derivation, we have that the optimal detector for any digital pulses, we can use what is so-called a matched filter. So if we have a receive signal that comes in, all right, if in general, we need to construct the type of match filter to the transmitted pulse. If the transmitted pulse have like multiple of them, many of them, A simple way is to construct many matched filter. Okay, for each pulse, it's like to detect each pulse separately, right? We can have a bank of matched filter, and this matched filter is just the specific pulse. The impulse response has a shape of the pulse that are transmitted, and then followed by A to D, and then comparators. So very, very specific. Okay. So let's take a look. What are the shapes of the mesh filter when we take a look at it? Okay. We will look at one or two examples so that we understand what it means. Okay. Okay. So let's go to example. So if we look at for this example, okay, let's find the impulse response HOT of the meshed filter for the meshed filter below, or for the digital pulse ST below. Okay, so let's do two parts. Let me do part A first. Okay, if we transmit, let me say this is the pulse that has amplitude 1 from 0 to T. Okay, so in order to obtain the impulse response of the meshed filter, first step is to perform a flipping. Okay, first we flip with the vertical axis. Okay, which in essence we find S minus T. So that's all we do. Okay, just flip compared to the vertical axis. And then next step is to shift to the right, shift to the right by t seconds. Okay. So this t is the big capitalized T is the T is the period of the bits. Okay. So we just move it to by t seconds. Okay. So in a way, this is for NRZL, no? But for bit 1, right? We can do similarly for bit 0 for NRZL, no? We will get the match filter as, can you guess what you will get? Let H0I, let me call this H1, H1T, no? And then let's H0T for bit 0. You get the same thing, okay? So from this example, you see that for NRZL, the match filter looks the same as the pulse itself. Okay, if you have pulse for bit 0 like this, you need to use the match filter like this. If you have the pulse at bit 1 like this, you need to use the match filter that has the impulse response that looks like this. Okay. Okay, let's look at part B. Let me do another example. Let's say that we have a Manchester pulse for bit 0. Let me still use -1 and 1, no? So this is the T. So this is T over 2, okay? Let me call this S0T, okay? So we can do the same thing, okay? First, to find the match filter, we have to flip with the vertical axis. Oh, sorry. Okay, when we flip it, what do we get? Pure. Flip with the vertical axis.
Uh, how can I say?
From -t to -t plus to -t over 2, what amplitude do we get?
Uh, how can I say?
Okay, during this period,
Yes.
during this part, what do we get? Positive or negative?
Positive.
Okay, we just get positive. Okay,
Yes.
and this part we get
It's in
negative.
negative. Yes.
Yeah, and then when we shift to the right, we just get a flipped version of, oops, sorry. We just get the flipped version of the pulse S0.
Zero. Yes.
Wait, sorry, I think this is pulse 1. In another class is pulse 1. Okay. So we just get something like this, right?
Yes.
Okay. Yeah. So that's why we call matched filter. Okay. And okay, so that's what it is in general. So when we have a system, a simple system that we transmit any pulse, we need to use a matched filter like this, and then followed by the A to D and then threshold detector or comparator. If the pulse is just a positive like this, like an RZL bit 1, we use a matched filter like this. Okay. But in practice, because there are two types of pulses for binary systems. For binary system, so on the receive side, we have to have a two matched filter. Okay. You can say one is S1 and then S0. I think maybe it's better, no? Depending on the definition. Okay. So we need two matched filter, one for bit 1, one for bit 0. Okay. And oops, sorry, let me take a look how it is how it is defined here. Maybe it's a bit different from the way I define. Okay, so on this picture, I think they define this as for bit 0, and this is for bit 1. Okay, so when on the receive side, basically we have a bank of matched filter. We call this as a bank of matched filter. Okay, to detect each bit separately. Okay, and then followed by A to D. And after that, whatever we have, we just compare with each other. Okay, and if Z1 Z1 is for bit 0, Z2 is for bit 1, we just compare which one is higher, and we make decision accordingly. So this part is called decision. Okay, and for AIT here, the AI hat is the decision. We just make decision here depending on which one is higher. Okay, if Z1 is greater than Z2, we make decision on 0. If Z1 is less than or equal to Z2, we make decision on bit 1. Okay, so basically that's what we do. Okay. So let's have another example before we have a short break, okay? So let's take a look at this example, okay? I don't think I have time to go through all this convolution stuff. Anyway, mesh filter, when we look at how the time domain goes, is in general is a little bit more complex than the other structure. We will look at it after the break, okay? But let's look at this example first. So this is an example that let's we want to look at how the signals look like at each step on the receive side. Okay, let's say that on the receive side, we consider at one time we have these positive amplitudes. Okay, and this is for NRZL system. Okay. On the receive side, we have the mesh filter for bit 0 and bit 1 separately. Okay, so we don't make decision yet. We just let this pulse go through two branches. Okay, so let's look at the bottom branch. It's a bit easier. If so, what is the output at the bottom branch? The output is this one is Z2T. Okay, let me use maybe okay, red color is fine, and the top one is Z1T. Okay, So the output is just convolution of the received signal and the impulse response of the meshed filter. Can anyone tell me what do we get as the convolution of two squares with equal size? What do we get? I think I need to rely on Thirarat. What is the convolution of two squares with equal size? Can you remember?
We get the same.
We get triangle. Yes. I don't have time to go through the convolution because it's in the signal and system class last year. Okay, but convolution is basically you can fix one signals like this, and then you flip the other one to the left hand side. Okay, and then you move this the flipped version to the right hand side. So in a way, it's like this. You flip S. You flip the signals RT and then you move it to the right. Okay, the overlapping region is what we have here. So when we flip this thing and then we move to the right more and more, we have more and more overlapping until both of them overlap each other. We have the maximum, okay, at t second. When this thing moves away from the maximum overlap to the right hand side, then we have lower, less and less overlapping until at 2t. Okay, so that's what it is, and the maximum here is just the overlapping energy, which is in this case I think is the t. Okay, so mesh filter is in a way is a way to collect energy of the received signals. Okay, so this is what for the output of the mesh filter for bit 1. And then similarly, if we flip this match filter, we get the same thing, but just switch the sign because it's just the linear operation. Okay, I think in this case it's it's t, no? Okay, okay. And if t is equal to 1, here you get 1. Okay, I think I intentionally set the time to be 1 second just for simplicity. Okay, and then when we do the sampling, we sampling at every period. So here we get 1 or minus 1. Here we get a 1. Okay, and then we make comparison between Z1, is it more than or less than Z2, and we make decision accordingly. Okay, so these the numbers can switch depending on what you use as the mesh filter at the front. You can flip these two, no problem. Okay, if you flip, these numbers should switch as well. Okay, so in here you'll see that here we have Z1 as minus 1 and Z2 as 1. Okay, so we see that Z2 is larger than Z1, so we make decision that the transmitted bit is bit 1. Okay, so if you receive many signals, that's all we do for each period. Okay, so we need to know which period to do. Okay, okay. Lastly, before we take a break, I wanna look at this a little bit more. If you do a convolution of two rectangles, but different size, let's say one is 1 second, the other one is 2 second. Okay, so in this way, in this one, you get something similar to triangle, but you will get a I don't know how it's called, this thing. Okay, so this is 1, 2, and 3. Okay, so it's basically just overlapping area of one over the other when you move. You can fix one, either one, for simplicity. Let's say you fix the right one and you flip the left one, and you just move it, and you just move it. You just Okay, and you just move this the flipped version of this thing. You just move to the right, and the more it overlaps, the more it travels to the right, it overlaps, you get more areas, right? When it passes by, suddenly at some point it will go down. Okay, so in a way, matched filter helps collect energy of received signal. Okay, so please review on the convolution and so on. Okay. Oh, okay. Let me go through a few more slides, and then two slides, and then we take a break, no? Because they are still related. Okay. Okay. So, for binary system, we can also reduce the number of meshed filter so that uh, we don't need to use two of them. We can use just one. Okay. So from previous example, if we have the pulse as S1T and S2T, as for bit 0 and bit 1 for NRZL, okay. Uh, you notice that if you look at the decision here on the right hand side, okay, instead of comparing Z1 greater than or less than Z2, we can move Z1 to the left hand side, okay, and then we compare with 0. Okay, we can do this. Okay, so it means that because Z1 is the sampling of the output from mesh filter of number 1, and Z2 is the sampling of the mesh filter of number 2, right? Then we can, so instead of having to match filter, what we can do is we can do it like this. We have RT comes in, and we can pass it through H0T minus H1T. Okay. And this is because if we look at it before sampling, we have Z1T minus Z2T. This is just integration of RT times H0T minus H01. Okay, or not times, convolution and dt. Okay, so we can do it like this instead. Okay, and whatever output, we just go through A to D and then comparators. This is for binary system, and make decision for transmitted bits. Okay, but for H0T, for NRZL, it's just S1T, right? They look the same, and S1T is S2T. This is from previous definition, but we can switch around, no? So it means we can just if we subtract S1T and S2T, what do we have? We have like this: minus one is minus two, right? Okay. Okay. So it means that uh, uh, we can have a mesh filter like this. Okay. And A to D. And then make decision whether it's more or less than 0. Okay. Let me call this as a Z. We just compare it whether it's more than or less than 0. And then we make decision. Okay. And also you can flip this thing. I don't need to put -2, I can put -1 because here we only check the sign, okay? I can flip this from negative to positive, but then I have to switch between these two numbers, okay? So that's the way to reduce number of matched filter. So we can do the match filter in the Simulink like this, okay? So for NRZL, we can just transmit like what we transmit. We add noise, and then we can just use the one filter, and we define it as the matched filter. Okay, that's all. Yeah, we can define this as match filter because in this case you can see that the match filter here is just a constant value, right? Okay, but in Simulink we will switch. Instead of having this as a negative, in Simulink we will have this as a positive and switch this. So we'll do this instead. Let's say big T is 1, no? And we'll do this instead. Okay. So we can just define the filters as ones, and depending on how long this is, I don't know. Okay. Depending on how many sampling you use for each bit. Okay. Okay, let's take a break and then come back and we finish the remaining maybe less than 10 slides, okay? We'll look at another structure of the optimal filter, which gives the same result as the meshed filter, but I think in general it's a bit simpler, but we should know both anyway. Okay, so let's take a break about 10 or about 10 to 15 minutes and come back. I think we have time, and then we will look at the Simulink program. Okay. Okay. See you in about 10-15 minutes.
See you.
If you have question, look at this, and when we come back, please ask question. Okay. Okay, you have any question before we start? We go to the remaining slides. Okay, so okay. So this is a system that we will work on Simulink today. I just sent you the Simulink file. So today you don't have to construct anything. You just play with it, okay? And I think in the system it has more things because I also connected together with another blocks, which is called bit error rate count. This is another block that I put in that file, okay? So we will compute like the bit error rates and so on. And so we will adjust the SNR in the system by adjust the sigma or sigma square in this block, okay, to change the EB over N0, okay. So what we will do in this lab is we will vary this EB over N0 in decibel, and we will test the system and see what is the bit error rate that we obtain at the back. Okay. Okay, before we go to the fun stuff, let's finish the slide. Okay, we have 10 more slides. Okay, I want to talk about this briefly. Uh, Sometimes when we transmit the pulse, we don't transmit with the square pulse, especially when we have to transmit the data through band limited channels. So what we can do is we can use this pulse shaping technique, okay? And this is the important for channels with bandwidth limited, okay? For bandwidth limited channels, this will be very important, okay? Because as you know earlier that for square pulse, you know, if you look at the spectrum of the input, the bandwidth, it goes forever, right? It goes unlimited, okay? But if you have the communication channel that has bandwidth limitation, then some of the spectrum of the input data pulses will be chopped off, will be eliminated anyway, okay? So in such case, uh, this is one of the one of the most common filters for pulse shaping. Okay, so basically, instead of sending 1 and -1 as a square pulse, when we send it through these raised cosine filters, okay, then you have the pulses that looks like something like this. Okay, so each pulse look like this, and if we have pulse 1, it looks like this. Okay. Okay. For pulse 0, we have something like this. Okay. If you have the third pulse, they just overlap. Okay. We will look at later. But basically, if we use the pulse like this to represent bits, okay, this is called raised cosine pulse. Okay, it's controlled by the parameter called beta. Basically, it's a sinc function. Okay, but maybe it's like a modified shape of the sinc function. Okay, by the cosine and this term on the right hand side. When we let beta is equal to 0, it is the same as sinc function. If beta is equal to 0, this is just sinc function. Okay. and the shape is here. Let me see, maybe a bit difficult to see. Ah, this one. This is beta equal to 0. If you increase the beta value for the raised cosine pulse, in particular, if beta, normally beta is greater than or equal to 1, less than or equal to, greater than or equal to 0, less than or equal to 1, okay? So when beta goes up like this, so for the main lobe is not so different, but the difference is in the secondary lobe or the side lobes, okay? So normally when beta goes up, the peak of the side lobes will peaks of the side lobes will decrease. Okay, for example, this is beta equals to 0, right? And then we have beta for 0.25. Okay, if you the red color is beta is equal to zero point 0.5. Okay, and if you look at the spectrum, this is what we have. For beta equal to 0, the Fourier transform of the sinc function is just a square pulse. Okay, so in terms of spectrum, this signal has the limited bandwidth, okay, of RB over 2 or R over 2. Okay, if we increase the beta value to be 0.5 or to be 1, the bandwidth will increase. Okay, so if beta equal to 0, the bandwidth is at R over 2. If the beta is equal to zero point 0.5, the bandwidth is 1.5 times R over 2. And if beta is equal to 1, the bandwidth is equal to R hertz. Okay. So by the use of beta, we can control two things. On the time domain, we can control the peak of the side lobes. And then for the spectrum of the signals, we can control the bandwidth. The larger beta, the more bandwidth we can have. Okay, but we can still control the bandwidth. If we only use the square pulse for transmission in time domain, we cannot control the side lobe except changing the bit rate. Okay, but still you still have side lobe forever for the square pulses. Okay, so for this part, this is the spectrum of the raised cosine function. Okay. And let me see. Okay, and another pulse that we can use is called raised cosine pulse. It's called root raised cosine pulses or filters. Basically, is the square root of the spectrum in terms of spectrum. The spectrum of the root raised cosine pulses is the square root of the raised cosine pulses from the previous page. Okay. And I'm not going to go deep into why it's like this, but it's quite complicated in terms of, to write specific formula for time domain or for frequency domain. For frequency domain, it's easy. It's just a square root, but for the time domain, it's like this, okay? So in MATLAB, maybe not this lecture, but maybe this lecture, we try to use it in the Simulink, okay? But in MATLAB and Simulink, they have a block by itself that we can utilize. Okay, and so for root raised cosine, why do we use like this? Because for root raised cosine, when we implement in a system, this is what we do. So we put the pulse for the root raised cosine for the data bits. Okay, then we just get like something strange. And on the receive side, because the root raised cosine is a it is an even function, it's a real and even function. So the mesh filter looks like the pulse itself. Okay, and we still can use one mesh filter, and then followed by all these. Okay. Okay, but if the channel is the ideal, no bandwidth limitation, there's no need to use this type of power shaping at all. Okay, but in practice we have to, because the channels will have bandwidth limitation. Okay, but basically what we do here is, so if we look on the in terms of spectrum, for the root raised cosine, the spectrum is square root PRCF. Okay, and for the matched filter, because it's the same shape, in terms of spectrum, we have P square root P of RCF. Okay, so that means that equivalently, from on the transmit side and on the receive side, the pulse that we use is just the root raised, is the raised cosine pulse. Okay, because the multiplication is what is the resulting filter. Okay, so that's all. And next one is, if we have a non-binary system or MRE system. Okay, in this case, we cannot reduce the number of meshed filter that we use. We have to use M meshed filters. Okay, and this is the structure. So for the first match filter is a match filter that matches the symbol one, and then the next one is a match filter that matches symbol number, the pulse of symbol number two, and etc. to the pulse M. Okay, and then we have a to D for each bank. We call this banks of matched filter. Banks is just a series or sets of, and then the values at the output, whichever one has higher value, we make decision for that specific symbols. So we have decision rule like this: select Si, which gives the maximum Z, or output of the match of the A to D. Okay, we select the pulses or the symbol that is the maximum value of all the A to D outputs. Okay. So that's what we do. Okay, so the remaining slide, I will talk about another structure alternative to mesh to filter. Okay, so let's take a look at it. It's much simpler actually. Okay, okay. This structure is called correlators. Okay, as you know from the previous lecture, when we say correlate, it means if we correlate two things, like let's say we correlate receive signal and some pulse, it means we multiply together and we integrate within the period or time of interest, whatever it is. Okay, so this is called correlators. Okay, okay. So let's derive what is the correlator quickly. So from the meshed filter, the output of the meshed filter is ZT integration of the received signal multiplied with the meshed filter. Okay. And if the mesh filter has the impulse response, let's say HT, I write it in general. So ZT is actually RT convolution with the impulse response of the meshed filter in general, which is equal to integration of R tau H of T minus tau D tau. Okay. And for the causal filters, okay, and If we look at it in terms of for the causal filters, okay, for the causal filter, it means h of t uh, is equal to 0 if t is greater than 0. Okay, this is in general. Okay, or we can say that for the causal filter, h of t is not equal to 0 if t is, oh, sorry, uh, ht is equal to 0 if t is negative, is not 0 if it's positive. Okay, so we can think of ht that looks like this. This is an example, okay? And this is time domain. Just an example, no? Example. So at t less than 0, ht is 0. Ht can be non-zero only when t is positive. Okay. So if we look at this term, okay, so we can say that st minus tau is not 0 if the arguments t minus tau is greater than 0 or tau is less than t. Okay. So that means when we do integration here, we have to integrate from 0 to t because we integrate with tau. Okay. And okay, so what else? So I'm gonna derive this by putting in uh, we know that h of t is equal to s of uh, large t minus t. This is from previous slide for any mesh filter of the pulse st in general. So here I can write it as integration from 0 to t r tau, okay, and multiply with s of t minus whatever argument here, t minus tau, and then d tau, okay. And this can be written equal to, if I look at the output of the a to d, I can look at z of t equals to t. Okay, this is at the a. Oh, sorry, I don't need. Maybe I write it down here. Sorry, this is at the output of a to d. So here, let me leave it at it as it is. Okay. So at the output of the a to d, I have z of t or zi, okay, uh, which is equal to integration of r tau s of t minus t, let t is equal to capitalize T. I have t minus tau d tau, which is integration from 0 to t r tau s of tau and then d tau. Okay. And for t is equal to capitalize T, then I have integration from 0 to t r tau s tau and then d tau. Okay. Or I can write this as zi is equal to integration from r. Now I can put any arguments because they are all the same. But let me write it as t, so that is a bit easier. Okay. And that's all. So it means that the output of the matched filter after the A to D is equivalent to this term. Okay. So it's simple, meaning that we can look at this structure instead. Okay. So instead of so alternative to the mesh filter where you have RT and then you pass it through match filter S of t minus t, and then you do A to D, or you get whatever, and then you do A to D, and then you get ZI, and then you make decision. Okay. So alternatively, we can do this. We have RT. We can just multiply with SIT that we are interested, and then we'll get ZI. Okay. And then we do comparators and make decision. Okay. So in general, it means that for correlators, for binary system, for NRZI, we can just have this. Okay. So this multiplication follow, oh sorry, multiplication and then followed by integration. Okay. So these two things constitutes what is called correlators. Okay. And we do it for one bit at a time. This is for binary. Okay. So sometimes we call this as integrator, integrate and dump, meaning that we integrate some values of R multiplied with S for one bit, and then we throw away, and we do it all over again. Okay. But the rest is the same, just the same structure. So, so for binary system, this is the what one we can do alternative to matched filter. Just use two correlators. Okay. And here we use the same decision comparators. Okay. But we can also do the similar reduced circuit by, instead of using two correlators, we can just subtract one's pulse from another, and then we only use one integrator only. Okay, meaning that we can only use one correlators. And then for comparison, we can just do, let's say S1 represent bit 0, and bit 2 and S2T represent bit 1, we can just put 0 and 1 here. Okay. In statistical studies, sometimes instead of putting bit here, they put hypothesis 1 and hypothesis for pulse 2. So it can also be done as well. Okay. So let's look at another example for correlator. So I think this one is already oh, I see, I see. So here you can see that because we use the S1 minus S2, okay. So here we can reduce this the circuit a bit further, okay. So if we subtract S1 from S2, we have this shape, right, from previously, right. So if we do correlators with the receive signal by multiplying this with the S1t minus S2t, okay, which is minus 2. And then we do integration from 0 to t. And then we compare output, whether it's more or less than 0. And then we make decision accordingly, okay. We can reduce even further, okay. So we will notice that instead of multiplying with any negative values, we can multiply it with positive value, like 1, okay? Which we don't need to write it even because it's just multiplied with 1. And then here we can just leave it as it is, but then we need to change the decision at the back. Okay, instead of having 0 and 1, we do 1 and 0. Okay. So in a way, we flip the decision here. Okay. And this is what we will use in Simulink. Okay. We don't even need to multiply with anything. Here we don't even need to multiply. For this type of NRZL, we can just sense whatever RT to the integrators only. Okay. So equivalently, that's all we can do. Okay, but this is only for binary system where we can reduce number of circuits like this. Okay. Okay, and the last two slides. This is for Simulink. I don't know today. Maybe we don't have time to do in the lab, but maybe I ask you to at home. So simulate in Simulink, we can do correlators by whatever receive signal RT. We just multiply with the same pulse, which is in this case S2T for bit 1. Okay, and uh, so so and then we is followed by integration, which is here. Okay, so this part is correlator in Simulink, and the rest is almost the same, no? Just A to D, and then compare with 0, and so on. Okay. Okay. So let's. Uh, if we don't do if we don't do correlator today, we'll do mesh filter, and then we play with correlator next time. Okay. And lastly, last slides. So for uh, if we have M-array system or non-binary, okay. If you don't have any, if you don't do any like simplification, we can use a bank of matched filter. Okay. Meaning that for each pulse, for each symbol, we just have we need to have M correlators, basically. Okay. M correlators. Okay, and then we make decisions similarly to the match filter as well. Okay. Okay. Any question before we go to the Simulink lab? Yes, no? No question at all today? What's going on? Mhm. Okay. Tananpat, any question today? Maybe from last time?
No, teacher.
Oh, so you understand everything? Okay. Okay, so let's go to Simulink today. Okay. I sent you the file already, so we can take a look together. Okay. So let's start your Simulink program. Okay. So this almost is for the whole system, and this is what you need to do. Actually, could you possibly turn on the camera, everyone? I think it's a bit too inhumane to just look at nothing for many hours. Okay, yeah, please turn it on. Okay. And the lab is quite short, but maybe we need to look at it together, so that it's not it's not difficult. Okay, so this is the lab today. Okay, so now that I'm talking about it, please uh, open the Simulink program and then load the file. They are in the Google Classroom. Okay. So in this lab, we will study the bit error rate performance of NRZL modulation through AWGN channel. So this system has already been given to you, so you don't have to connect it. Okay. And we will compute the sigma square. Actually, let me take a look in the Simulink. Okay, this is variance, no? So it's sigma square. Okay. We can, okay. So we will modify the SNR by changing this value. Okay. But first we need to compute the variance. Okay. So in this table, maybe you can compute sigma square for maybe one value, let's say 9 decibel. Okay. Let me go to the uh, to the note. Let me see. I think they have the whiteboard, right? Okay. Yeah, let me start the whiteboard so I can write it. Actually, I can write on the. It's okay. I can write on the PowerPoint as well. Okay. So how are we going to adjust the SNR? So let's take a look together. So in Simulink, this is how we're going to, let me take out this line first. Very simple formula actually that we are uh, computing for sigma square. You can use MATLAB to compute, okay, but let me write down the formula for SNR, okay. So how to adjust the SNR, the EB over N0, okay. So in the Simulink, what we will have is for EB, we set it as 1, okay? Because what we do is, let's say we have a pulse, positive pulse for bit 1, okay? If we have 100 of them, okay? This energy, what we have is energy EB is equal to energy for each discrete signals, which is 1 plus together 100 times. And then we divide it by 100, okay, which is 1. So that's what we will do, okay. And actually, I'm sorry, actually, the amplitude has to be not 1, but it has to be 1 over, let me see. It has to be 1 over square root 100, okay. So that when we compute the energy, we have, so when we compute the energy, we have the square pulse of each one. So we have 1 over 100, okay, and plus together 100 times. This is what we have, okay, which is 100 over 100, which is 1. And so to adjust the SNR, we have to adjust, we will adjust the noise part, okay. So we can use this formula. If EB over N0 in terms of decibel is equal to 10 log base 10 of EB over N0, okay. You can replace EB in this case with 1 because we will set EB as 1 nevertheless, okay. So, and also from sigma square is equal to N0 over 2, which is one-sided PSD, okay. So we will have that, what is it? Okay. So we can have that EB over N0 without log is equal to 10 to the 0.1 multiplied EB over N0 decibel, right? Okay. And if I let EB equals to 1, okay, I have 1 over N0, which is 10 to the 0.1, and multiplied. This term I can call SNR decibel. So that is a little bit easier to see, you know. And what is N0? N0 is 2 sigma square, right? Okay. So this is 1 over 2 sigma square. Okay. So I can have that 2 sigma square. I can just flip this term. I have 10 to the minus zero point 0.1 multiply SNR decibel. Okay. This SNR decibel is just EB over N0 in terms of decibel. And sigma square is just 1 over 2 multiply 10 to the negative zero point 0.1 multiply with SNR decibel. Okay. Okay, so you can use this formula to find sigma square. Okay, so I want each of you to compute sigma square for different SNR. Okay, so maybe Tirarat. So for you, Tirarat, you can find the sigma square for 7 decibel. Okay, you can just replace 7 in this formula here. Okay. For Tananpat, let's do 8 decibel. Okay. And tell me what you get. And also Pio, are you here? Pio?
Yes,
Okay
yes.
then. For you, let's do 9 decibel. And tell me what is the sigma square. Okay. Okay. So this is like a teamwork. Okay. You can use MATLAB to compute. Okay. You can just replace in the formula. Okay. So what do you get, Hirarat, for 7 decibel?
0.099.
Okay. How about Tananpat? What do you get? How about Pio? What do you get for 9 decibel? Tananpat, you get sigma square yet?
Not yet, teacher.
Do I have to compute for 1, 2, and 3?
Yeah, if you have time, just fill it in. We'll use it later anyway. But you can use MATLAB, just one line as well. What do you get for 8 decibel, Tananpat? Why so slow? Just put number 8 here and compute. You don't have a calculator? How about Pio? What do you get for sigma squared? Hey, Tananpat, you don't get sigma square yet? Tananpat, can you hear? Okay, let's pass then. Okay, let's go to Simulink. It's incredible. Okay.
0.0000125.
What do you get? You just use calculator, just a little bit. What do you get, Pio? What do you get, Pio? Can you say again?
0.0629.
What? I don't understand what you said. 0 point what?
0.0629.
Huh?
0629.
0 dot and then what? zero six
zero two
zero
nine
six two
two
nine
nine.
nine, right? 9, right?
Yes, yes.
Okay. How about Tananpat? You get it yet? Eh? She disappears. Okay. You don't know how to compute this? Okay. Oh, unbelievable. Okay. Let's go to the Simulink then. Okay. So before you do anything, let me check first whether we have the right. Okay, here I use the system that I use filters to build the transmit side. Let me change color, so that we are on the same. So we use the same color for transmit and receive side. We use different colors. Okay. So the first part you should do is let's make this variance very small, okay, to constitute very, very high SNR. Okay, let me do something very small like this. Okay, just do it. So we have very, very large SNR. Oh, cannot read it. Okay. And if you notice, if you double click in the numZ here, I put okay, I put 1 over square root 100. Okay. So this will be the same, no? I don't change anything at this point. Let me just check whether it's correct or not. So here we have 0 and 1, and then we have positive, negative. And then on the receive side, here, at this moment, I don't have any matched filter yet. So you notice that whatever I receive, I just sampling it, okay? I just do sampling and then make decision. That's all I do, okay? So let's try to run this system and then see what are the, here, if you take a look here, this is called an error rate calculation blocks. Let's take a look together, no?
อาจารย์คะ
Yes, yes.
What is the double box like
Oh.
the name of it
One moment.
I can
One moment. What did you say?
like the name of the double box in the system
Double block in this. Wait. I sent. Oh, I sent you the file in the Google Class.
I cannot open the file so I just like adjust the previous lab
Oh, I see. Okay, so for the double, I think it's a type change. Let me take a look with you. Let's go to the library browsers. Okay. The library browser, the type change, I think is in, oh, I don't remember. Wait. Let me look for it quickly. Math. Okay, let's search then. Here, right? Is it this one? Let's take a look. Yeah, I guess this is the one. Yeah, there is data type conversion. Yeah, I think you can search with data type conversion. Tananpat, so did you get sigma square finally? I think she doesn't hear me today. Yeah. I think you can just do data type conversion.
I get 0.079.
Okay. Just use that number for your lab. Yeah, I think this, yeah. See, Tirarat, do you see on the screen? So these are the data type conversion. I guess you can use one of these. Yeah. They are in different parts. Okay. The reason I need to use this is because uh, here this is a logic. This is also like 0, 1, but this blocks the error rate calculation block. It requires the type, the double type as input. So I need to force change the type of data here. Okay. Pio and Tananpat, can you open the Simulink file that I sent, or you cannot? Mhm.
No, I'm building it my own.
Oh, really? Okay.
Yeah.
I just want to reduce time by giving you the file, so you don't have to do it. Okay.
So the block of convert and double is the same, right?
Yeah, yeah. But when you change to case double, then it changed the word double itself here. See? Okay.
And for how about the output of the error rate calculation?
Display. What do you mean the output? It has an output here.
Like for my system, it doesn't have the output for the error rate.
Maybe you have to double click it and then see what's the output here. It can be workspace, it can be data, depending on what you want. Okay. So whichever block doesn't have this type of port, you can double click and then see what you can adjust. Okay. Okay. You got it, everyone? Use the Simulink file I sent if you can open it. I think it's is it .slx? Yeah, this is the file. What's the file type? I thought it was the double, is the .slx, isn't it? Yeah, yeah. You can open it with MATLAB 2020 at least, or lower is okay. Okay, and don't forget you need to change the energy here. Okay, is everyone ready? Don't forget here in num_z you have to make it ones and then 10 and then square root 100. Okay. Okay. If you upsampling more than 100, I don't think you need to do more than this. If you upsampling like 50 or 20, you need to change the numbers in here, okay? To have energy of 1. Okay. So everyone finished? If you finish, just tell me. Tirarat, you finished? The building?
Not yet.
Okay. I give you maybe 5-10 minutes then. Okay. Also notice that on the scope, I put in many outputs so that we can take a look later. Okay. We will use this as a base to change the receive signal in terms of using matched filter or correlators. Okay. No hurry. We have lots of time today.
So I just record the bit error rate from the first value on the display box, right? The
Uh,
decimal one.
no, we will do together. Just wait. I'm waiting for all of you to finish. You can run it first if you want, but basically at the moment, because I want to intentionally set the noise level to be very low, right? By setting the variance to be super low, so I would expect to see the error to be zero. Okay, but you may need to run, like, instead of running like just 10 bits, it should run a lot. You try to run like 10,000, or I don't know, 10,000 or 100,000. Okay, then it's better. Okay, let me run for fun and see if everything is right. We should have zero error. Okay, because we have very little noise. So let me run it, and then, well, if everything is right, no. Wait, the number is supposed to run in here. It's compiling. Oh, I see. It's not. Okay. So see, now when it's running, at the moment I set the noise super low, so I would expect to see zero and it doesn't change, meaning that no errors yet. Okay, if you get something like this, it's a good sign that, okay, we calibrate the system quite all right. Okay, I think you don't need to run like me 10,000. It's just too much. Wow, it takes a long time today. What's going on? One way to reduce the amount of time by changing up sampling rate as well, or and then change the number in here. Okay. But then remember, if you change the sampling rate and all that, I think in noise you have to change as well, because in the noise block. Oh no, not noise. Okay, I guess that's all. Yeah. Maybe too much. Why is my computer so slow today? Did I put in 1 million by any chance? Let me see what I put. 100,000? No, here not so much. No. Okay, here's the time at the bottom. No, so almost finished. You can put 1,000 is enough. No need to put 100,000 like me. Maybe it's too much. Okay. So this is the first case where we set the system. Pure Tananpat, do you get this? You get all zero when you set the noise to be very low.
Yes.
Okay. So let me do one more. So now instead of having very low noise, let me play with the large noise. One moment, let me change simulation so that not so many, maybe 1,000 is enough. Okay. And let me change the noise level. Let me do zero point 0.5 or zero point 0.3. Okay. Just so that is a bit higher. Okay. And for point 0.3, what is EB over N0 in decibel? If you use the formula on the previous page. Okay, try to compute for fun with me, no? Okay, so in this case, I put point 0.3. Oh, actually, let me do this. Let me put point 0.1. I can compute in my brain. Okay, point 0.1 is 10 to the negative 1, right? So so 1 EB over N0, which is 1 over yeah. So it's very low SNR. Okay, low SNR. Let me run this, and you take a look here on the right hand side. Okay, let me change color so it's easy for me to say. Okay. Let me change to oops. Let me set it in light blue. Okay. So let's look at in the light blue display and see whether the number goes up. I see. Earlier I didn't put it large enough. This is the number I ran. Okay. Uh, Let me run the system now. Let me do 1,000 bits. Okay. So it doesn't take a long time. Okay, so take a look. This is how it happens. Okay, already very, very quick. No, finished already. So I run 1001 bits. There are 370 errors, and the bit error rate is 0.3696. Okay, so this is what we do. So what we are going to do is, for this system which is not a mesh filter, so everyone you can work together. So so let's compute the variance for EB over N0 from 1 decibel all the way to 10 decibel. Okay. Or if you want, you can run the variance for the values that you compute earlier, which are 7, 8, and 9. Okay. And also, I think, take a look at this block, error rate calculation, everyone. Let's take a look at this block. I think we can set one condition here. Let me see. Let's take a look together at this block. Everyone, look on your screen. Thananpat. เอ๊ะ G วันนี้ทำไมเรียกแล้วเหมือนไม่หันมาดูเลยอ่ะ
เน็ตมันช้าค่ะอาจารย์
Okay. You can do this, okay? If you click on stop simulation like this, take a look everyone. If you click on stop simulation like this, you can set the target number of errors, okay? So that the system stops by itself. It stops running bit error rate whenever you have 100 errors, okay? And you can put the maximum number of symbols that you run. In this case, I set as, let me set as 10 million. Because when we run at 10 decibel, maybe it takes a long time, okay? Okay. So, yes, any question? Any question? Oh, you can put 1 million, no problem, whatever you want, okay? I'm gonna do this. Okay, so I press okay. So take a look here, no? So what you will do is when you compute the variance for the whole table, you put variance here one at a time and then compute bit error rate. You fill in the table until it's finished, okay? To get what I'm saying or not? You get what I'm saying? Okay.
The value that we record for bit error rate is
Here. Yeah.
the first one where
Yeah. Or you can compute yourself. Yeah. Also, there's a little bug here, but I haven't had time to change it. We're supposed to have 1,000 bits here, right? Yeah. So let's take a look now. If I run again, but I don't run with 1,000 because I set it. I can set these as a very large errors, very long. Okay, and then I run it, and the system will stop by itself. Okay. So let's take a look one more time. Okay, take a look here. Everyone take a look here. Now, when I run again, it stops at 100 errors. See, it stops here. And it stops after 273 bits and compute the bit error rate, okay? So this way, we don't have to change number of bits we run too much. We can just put like a lot here. Here I put like what? Like 1, 2, I put 10 million, just large numbers, okay. Okay. So this is part 2 and part 3, just to run, okay.
Okay.
And then you fill in the bit error rate, okay. One is done. you can plot the bit error rate curve in MATLAB by setting bit error rate is equal to let us compute SNR first. SNR decibel as 1 to 10, right? I think we do 1 to 10, no? And then bit error rate, you just add in here for 10 values. And we will plot as a semi-log y. We will plot as a log domain, like this. Okay. Why don't we do this? We divide work among three of you, right? Maybe Thirarat, you can do maybe Thirarat, you can do 1.357 decibel, okay? And then Thananpat, you run for 246 decibel, and then Pure, let's, why don't you run 1, 2, 3, 4, 5, 6, 7, oops, okay, I don't have too many values for you. Thirarat run to 137, Thananpat run 246, and Pure let's run at 5, 8, and 9. Okay. I want Thirarat and Thananpat to also run 8 and 9 as well. Okay. Maybe Pure you can run 10. It's gonna take a long time though. Sorry. Okay. How about this? And then we combine together in the uh, for the sigma value and also for the bit error rate. Okay. Okay. So if three PO, can you turn off the speaker for a short time? Okay. Also,
Sorry.
no problem. If each of you compute sigma square value for each of these decibel already, please tell me. We can put in this table together. Okay. Okay. Already 11:44. It's okay. We have time today. Okay, so all of you finished computing the variance value or not?
I'm not finished yet.
In MATLAB, you can use this command. Okay, let's say that SNR decibel is, let's say it's 6 decibel. Okay, I think the formula for sigma square VAR is 0.5 times what? 10 to the negative 0.1 multiplied with SNR decibel, right? Something like this, is that right? Yeah. Yeah, you can just do like this. Is that right? This is for var, no? Var. Okay. You can use the formula like this to compute. Let me take a look on the whiteboard a little bit. Oh, where's my whiteboard? It's gone. Oh, I see. I wrote it here, not on the whiteboard. Okay. So here is 0.5 multiplied 10 to the negative 0.1 times SNR decibel. So you can use this already very quickly. Okay. So what does each of you get for the variance? Let's put down together so we can continue from the next phase. Okay. What is 1? Sigma square for 1 decibel?
0.3972.
72. What how about 2 decibel? Whoever finish first, please you can tell me now. No.
0.315.
315. How about 3 decibel?
0.2506.
2506, right? About 4 decibel. What pure? Which,
0.1990.
which decibel? 5? Is it 5 decibel? How
Oh,
how many decibels?
5 decibel.
Okay, what's the variance? 0 what? 0
5
point
decibel or 4 decibel. I calculated all. 5 decibel. 0. For 5 decibel, 0.1581.
what? Say again. 0 point what?
1581.
1581.
81.
Okay.
For 4 decibel, 0.1990.
What? 0 point.
0.1990.
Okay. 0 point what?
1
1
990.
99. Okay. What 6 decibel?
0.126.
Okay. 7 decibel.
0.0997 for 7 decibels.
0 point what?
0997.
0997. Okay. 8 decibel.
0.079.
79. Okay. So the value is supposed to be lower and lower. Okay. Good. How about 9 decibel?
0.0629.
0 point what?
0629.
0629. Okay. And how about the 10 decibel?
0.05.
Say slowly. 0
05.
0.05. Okay. Yes. So each of you put variance here, these variance in the system, okay, and then run a little bit error rate, and then tell me what you get, okay. Okay, you need to change the variance here, okay, on the left hand side. Well, for some of you who may be too lazy, later on, maybe you can change this block to decibel number, and then you use a MATLAB function to convert to VAR automatically. I think you can do that, no? It's also simple. Maybe I do it with myself for fun, okay? Maybe I can get it. Let me see. I can use MATLAB function, right? Function. Yeah, I can do it like this. No, I'm super lazy.
See, yeah.
If I am too lazy, I can do this. Let me put in as 1 decibel. Oops. Okay. And then in here, I use the function here as y is equal to I'm too lazy to watch that. Okay, is that right? Yeah, I can just do this, right? And I finish. Okay. And if I double click here, I get this function. That's all. I don't know whether it's correct, but let me let me take a look. Well, I hope it's correct. Okay, so now when I want to change the decibel, I just do here, I guess. Let me look at the library browser. Maybe I have a display so that I see things. Let me check my bar quickly whether it's correct. For 1 decibel, let me run. So okay, so I use MATLAB function to compute the EAR. I get 0.3 millisecond 2 for 1 decibel. Is it the same as what you said? Ah, same thing. Okay. So now because I get lazy, then it's easier for me. I don't have to type too much. Okay. Then I can just run and run. Let me run to 2 decibel for fun. Actually, let me run a high number, like 8 decibel, okay, just for fun. It's gonna take a long time. Let's see. Okay, let's take a look together. What? Something is wrong. Oops. Okay. Something is wrong.
We have a error rate. We have a store simulation error rate. That's why we are first, I think.
Say again.
Set store simulation counter in error rate calculation. So two pairs. When I disable the store simulation,
Maybe you need to reset the port. Reset. Actually, it should start automatically, I think. Let me take a look at it. Hmm. Hmm.
uh, Aja,
Yes,
when,
yes.
when I disable the store simulation point in the error rate calculation block, it's gonna take very long time.
Yeah, it will do it. It will do until the errors becomes 100.
Yes.
In your case, what's the error number now?
I disable this one. It's only 1%.
Which decibel? Mhm.
For 4 decibel.
4 decibels.
Yes.
But then, did you make these blocks correctly?
Yes.
Say again.
Yes. I need to add a stopping point. I should have stopped.
So this is 100 divided by square root 100, right?
Yes.
Ah, I see. Mm, I think I may know why. Yeah, I think we computed a bit wrong. Maybe we need to make the SNR very large. Okay. can we change the SNR in this case, because this is the, yeah, I think the SNR maybe need to be changed. Let's do this for some quick change, because I forget that this SNR, they are for the case when we use meshed filter. So let's do something like this instead. No, let's do maybe 3, 6, 9, 11, 13, 4, 13, 6, 9, 12, 15, 18, 21. And let's see, I don't know how the number will goes down, but let's look at these four first instead. I think it will be better. Okay. So if you want, you can set a system like this with me, so that is a bit quicker. Yeah, I forget that I forgot that this the SNR from 1 to 10, they are for the case for meshed filter, which will be much better. So in this case, let me try say 15 for fun. Let me say 15. Maybe it has to be very high, but anyway, let's try this. Now it start to go slow, to go lower. Okay, so maybe I should go even more. Let me try 21 decibel. Okay, 21 decibel, and then run simulation again. Okay, now it will be much better. Okay, okay. Good. Yeah, so let's change the SNR to something like this. Here, 27 and then 30th. Okay. For 369, maybe no need because 3 is very small. Let me try 6. Yeah, I guess 369 maybe too small. Maybe I change this to too small. Maybe change this to start from 9. It's okay. We can do this. Yeah. 3 to 30, but we jump every 3 decibel. No. Okay. Okay. Yeah. Sorry. I forgot that it's a different. Uh, it's a different SNR range of interest. Okay. So just for simplicity, please try to use function like this. So that is a bit easier. Okay. But this table don't throw away. Okay. We can use it later for the mesh filter and correlators. So they still can be used. Don't throw them away. Okay. But for the first part, let's use this instead. Does anyone get any bit error rate for some of these decibels by any chance? Tirarat, have you tried any of these SNR on this on the left table? Pure, Tananpat. Oh, I did 6 for you already, no? 0.379. 0.379. Okay. Oh, 5.9. Okay. Does anyone try other bit SNR together and tell me the numbers? So I can put in here. No? Tirarat, have you tried any of these?
I'm trying.
Okay. It's a teamwork, okay? How about Pure? Pure?
Um, no, yeah, please wait. My computer is hanging.
Okay. Yeah, try this. It's easier. No need to compute the variant in this case.
Yes. So I need to rewrite something.
Okay.
See and show you to you.
Okay. Yeah.
For 3DP, I got 04965.
Once again,
Zero 65.
0.965.
Yes.
965. Okay. So as the SNR starts to increase, we should see the bit error rate decrease. Okay. Okay. Any other decibel? Let me try 3 with you. Also, maybe we don't get the same numbers always, but we should have similar values because it's the random data. Okay. See, Tirarat, when I tried the 3 decibel, Tirarat,
Yes.
when I try the 3 decibel, I get 0.473. No need, it doesn't have to be the same as you, okay? Because it's random. But if we set more data bits, more and more, we will have more and more similar statistics. Okay. Okay. Has anyone done 9 decibel? What do I get? Pure, which one have you got? Tananpat, which decibel are you trying?
It works.
I get 0.3
Which decibel?
9 decibel, teacher.
Point what?
3891.
0.3891, right? Okay.
This
Next,
works.
anyone got the 12 decibel?
What is this happening?
Hmm.
Computers.
I think if you're interested, you can also look at the scope as well. I don't know whether it plots or not. No? It stopped plotting. Why?
Okay.
Why? I want to know why it stops plotting. Okay. Anyone got 12 decibel?
Oh,
By the way, for
Uh,
21, 24, 27, and 30, it will take a longer time. Okay? What is 12 decibel? What's the bit error rate?
0.T236.
Okay. Oh, it goes down very slowly. Hmm. Let me try 33 just for fun. How far it's gonna go down? Okay, I'm trying 33 decibel. Oh, I don't know how far it's gonna go. Let's see. No errors. It takes forever. Huh? Or maybe 10 million is not enough. Anyone got bit error rate for 15 decibel?
0.2096.
0.96. Okay. You don't need to get the same numbers, okay? Because we use different seed. 33 is just too much. Okay. Hmm. How about Hirarat? Which one are you trying? Which decibel?
18 decibel.
18? Okay, I'll wait for you, no? How about PO? Which one are you trying?
21. This way.
21? Okay, I wait for you, no? Thananpat, try 24 maybe? Oh, look at it. I tried 33 decibel, still zero. After all this. Hmm.
Oh,
Okay, maybe I try 28. I think. I think it's just too much. Should I stop? Yeah, when the error goes down quickly, we should uh, go at lower at not a big jump in decibel. Let me try 28. Okay, how about what is 18 decibel? What is the bit error rate? Not finished?
0.189.
189. Okay. How about 21 decibel?
0.0529.
Zero what? 0 point
0529.
0529. Okay. So for these numbers, in terms of bit error rate, we can write in terms of exponential. Okay. Sometimes we write like this, 10 negative 2, or we can write as 5.29 e minus 2. Okay. We can do either way.
Zero.
Okay, now I'm trying 28 decibel. Now you see that it's like 10 negative 4, right? I think we should try 28, 29, even 30. Yeah, 30 we should try. Yeah. How about 24 decibel? What do we have for bit error rate?
0.0113.
1, 3. Okay, or I can write it in terms of exponential as 1.13 times 10 to the negative 2 or 1.13 e minus 2. Okay, and after 24 decibel, it will start to decrease very, very fast. Now, how about 27 decibel? Can anyone tell me in terms of exponential number? Oh my god, I still have 28 decibel like this. It takes forever. But it's only, maybe because I put too much upsampling. Maybe in the future I should use less. Like maybe 10 is enough.
It's gonna take a while.
27, I get 0.008851.
Can you read it out in terms of the exponential number like this?
Okay.
It's easier to say.
Uh, 8.54
Yes. Times 10 to the negative
teacher.
4, not 3.
Oh, 3 teacher.
Okay. Couldn't sum that quick. Okay. How about 20 or 28 I'm doing. Okay. But it's so slow now. Now you can tell. I think it's about 2 times 10 negative 4. If you look from the screen, okay. I will just use that number just for simplicity. Okay.
Yes, you know.
Okay. Is anyone doing? So now we should do 29 or 30. Yeah, I think 29 is okay. No need to do 30. Just too much. Okay. So last one is 29 decibel. Okay. And then we will plot together. Okay. Or we can stop here. It's okay, because the our goal is to evaluate the session bit error rate for mass filter anyway. So this is only as a reference. Okay. So let's plot together what we have here. Everyone, let's take a look. Let's take a look together. This is gonna be what we plot. Okay. So when we plot, we'll do this. We will set the SNR decibel as whatever number we have, which is 3, 6, 9, 12, 15, 18, 21, 24, 27, 28. Okay. And we will write the error rate and then plot according to what we get in the table as well, which is 0.4965, and then have space 0.3759. Maybe I think maybe you can use comma in between numbers. 0.3891. So you notice that the bit error rate doesn't go down so quickly at the beginning, but once the SNR has increased drastically, then we have a much lower bit error rate. Okay? So for the number that are becoming lower, so let's say 5.29, E negative 2, I can just put like this, E negative 2. Okay? It will be easier. And let me stop this simulation because it still seems to be like 2.1, right? 2.1, 2.1. Oh, it keeps going lower. I don't know where to stop. That's why we set here the number of errors to be 100, so that we have enough error statistics. Right? So let me go down with 0.2, 0.002 like normal. Okay. So here 1.13 e negative 2, then 8.5 e negative 3, then 2 e negative 4. Okay, so we'll plot something like this. Okay, I'm gonna move this to the MATLAB command window just for plotting. If we put something wrong here, it will show error on the next page. Also, when you add in this number, sometimes you type it wrong and you get very strange curve. Okay. So what we are going to do is we are going to plot what is so-called the bit error rate curve. On the x-axis is the SNR, on the y-axis is the bit error rate, and on the x-axis is the decibel of SNR. On the y-axis, you plot as a log domain. That's why we put semi-log y. Oops, not semi, oh, sorry, semi-log y. Okay. So this is what we will get. Yes. Okay. And maybe I put a grid here so that it looks a bit better. Also, if you take a look, you will see that we don't have the x-axis and the y-axis. Let me put the x label. Hey, Pio, can you turn off the speaker?
Oh, sorry.
X label is gonna be E over N0, okay, in decibel. And then for the Y label, we will have bit error rate. Okay, so that's what we will do. This is what we will get. Okay, this is called bit error rate curve. On the x-axis is the what do you call it? SNR in decibel, and this is the bit error rate. So from now on, we will plot this type of curve and compare various type of modulation scheme or various system. Okay. Also notice that if you take a look here, are there any SNR that looks quite not so smooth? Here, right? Not so smooth, right? So we want a smooth, very smooth SNR, you know. And I think one reason we have not a very smooth smooth curve is because we set the number of errors to be 100. We can set as 1,000. It will make it much better. Okay. And also here at this is maybe 27. Who gave me the number for 27 decibel? Was it Pure or Tananpat? For 27 decibel. Here. Who gave me these numbers?
Me, teacher.
Yeah. So I think what is the amount of errors you have here when you run this 27 decibel? There's a reason why it doesn't jump, it doesn't come down smoothly. Okay. You need to have the numbers very small. Here I have 28 decibel. Now it's still 46 errors. So it's 1.96. Maybe it's better, right? 1.96 e to negative 4. Yeah. I think if I look at the graph here for 27 decibel, oh no, 26. I think 20. Wait, this is 24. Oh yeah, 27. It's supposed to be lower. I think it should be down here. Maybe 2 or 3 e negative 3. Yeah. Okay. You have to rerun it. Yeah. The graph supposed to be smoother. Okay. Okay, so that's it for today. So I want you to expand this system, but add match filter instead, okay, and run from 1 to 10 decibel. Okay, so this is the homework for this week. Okay. To add mesh filter, what you need to do is to add this. You just add this block here before the A to D. Okay? Add this block before the A to D. I think that's all. Okay, and the rest is the same. No, but for correlator is a bit more involved. You have to look at the slides for the correlators. You will have to add 4 blocks like this. Okay, but you play with match filter first, and then if you get the right bit error rate curve, then you can play with the correlators and you can play around. Okay. Okay. I think what we can also do is like this. Maybe let me go back to the homework. Okay. So there are 2 parts in the homework. Okay. So this is called part 2. So this is part B. So for part A, I want you to do this. Add match filter to the Simulink file. Okay. And run the Simulink for only 10 bits. Okay. And then plot the output each block so you understand what they look like. Okay, they're supposed to look like a how do you call it, triangle and then trapezoid, something like that, and then you run simulation. Okay, so please submit this lab, only part 1, to the system. I will set the time to 1 p.m. No, so that you have time. Kirarat, do you have any question? Okay, let me also stop the recording now. Any questions so far? Okay. If not, we will see each other next week.